Dalton's law of partial pressures. Dalton found that the total pressure of a combination of gases, P1 and P2, is simply the sum of their partial pressures. Consider a case in which two gases, A and B, are in a container of volume V. The pressure of gas A is equal to the number of moles of A times RT over V. Pressure of B is equal to the number of moles of B times RT over V. Dalton's law states that the total pressure P sub T equals P sub A plus P sub B. We define the mole fraction as the number of moles of the gas that we're interested in over the total number of moles. The mole fraction of A is N sub A over N sub A plus N sub B. Similarly, the mole fraction of B is NB over NA plus NB. The partial pressure of gas A is the mole fraction of A times the total pressure. The partial pressure of gas B is equal to the mole fraction of B times the total pressure. A sample of natural gas contains 8.34 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. If the total pressure of the gases is 1.37 atmospheres, what is the partial pressure of propane? The partial pressure of gas I is equal to X sub I times the total pressure. The total pressure in this case is 1.37 atmospheres. The mole fraction of propane equals 0.116 divided by 8.24 plus 0.421 plus 0.116. This evaluates to be 0.0132. The pressure of propane then is 0.132 times 1.37 atmospheres, or 0.0181 atmospheres. Many times gases are collected over water. In this case we have the decomposition of potassium chlorate into KCl and oxygen. The total pressure of the gas is going to be equal to the pressure of oxygen plus the pressure of the water vapor. A 2.10 liter vessel contains 4.65 grams of a gas at 1 atmosphere and 27 degrees Celsius. What is the molar mass of the gas? The molar mass is equal to the density times RT over P. The density is the mass over the volume. In this case it's 4.65 grams divided by 2.10 liters, or 2.21 grams per liter. The molar mass then, substituting in the density 2.21 grams per liter times the gas constant 0.821 times the absolute temperature 300.15 divided by the pressure 1. The molar mass is 54.5 grams per mole. This example shows you how the partial pressure affects the calculation. In a reaction, 0.500 liters of nitric oxide was collected over water at 19 degrees Celsius and 769 torr total pressure. What is the mass of nitric oxide collected? The vapor pressure of water is given as at 19 degrees, which is 16.5 torr. Remember that the total pressure is equal to the pressure of nitric oxide plus the pressure of water. Solving for the partial pressure of nitric oxide, we subtract 16.5 torr from 769, which is 753. PV equals nRT. Substituting for N, mass over molar mass, and solving for M, PV times the molar mass over RT. Substituting in 753 torr converted to atmospheres by dividing by 760 times 0.5 liters times 30 grams per mole, the molar mass of nitric oxide. That is divided by 0.281, the gas constant, times the absolute temperature, 292.15 Kelvin. The mass turns out to be 0.661. Here's a graphic showing the vapor pressure of water versus temperature. Notice that it's not linear. The table to the right gives the values of the vapor pressure at various temperatures. Kinetic molecular theory of gases. A gas is composed of molecules that are separated from each other by distances much larger than their actual size. The molecules have mass, but negligible volume. Gas molecules are in constant motion in random directions, and they frequently collide with one another. These collisions are perfectly elastic. Gas molecules exert neither attractive nor repulsive forces on one another. The average kinetic energy of molecules is proportional to the temperature of the gas in kelvins. The kinetic energy, remember, is 1/2 the mass times the speed squared. Gas diffusion is the gradual mixing of molecules of one gas with molecules of another by virtue of their kinetic properties. The rate of one compared to the rate of the other gas is equal to the square root of the molar mass of the second gas divided by the molar mass of the first gas. It's an inverse proportionality. Gas diffusion is the process by which gas under pressure escapes from one compartment to another by passing through a small opening. The rate of one compared to the rate of the other gas, 2, is equal to the time for a fusion of 2 divided by the time of a fusion for 1, inversely proportional. And that is equal to the square root of m2 over m1, molar mass 2 over molar mass 1. This graphic shows how gases stop behaving ideally at higher and higher pressures. If we increase the pressure of any gas, it stops adhering to the ideal gas law. If we're going to make calculations on gases at high pressures, we have to account for these deviations. One way of doing that is the van der Waals gas equation for non-ideal gases. Van der Waals corrected the pressure by a term an squared over v squared and corrected the volume by another term n times b. A and b are known as van der Waals constant, and the chart on the right shows A and B for various gases. We will not be calculating using the van der Waals equation, but it is important to know that such equations do exist for real gases, or that is, gases that behave really rather than ideally.